Now that we're familiar with the idea of parametric curves, we're going to apply a bit of calculus to these ideas. So we're going to look at things like finding tangents and areas and arc length and all that good stuff with parametric curves. So let's start with tangents. When we talk about a tangent, we're essentially talking about the slope of a line. So if we have our two functions that make up our parametric, our two parametric functions that define our curve, and they're both differentiable. So if we suppose that both x equals f of t and y equals g of t, that they're both differentiable. If that's the case, then we can find the tangent line at a given point on the curve. Okay, so if we want to find the slope, normally what we think of the slope is dy dx, but I want to start with one of the other derivatives, just one of the derivatives of either our x or our y. So let's do the y. If I start with dy dt, I can write dy dt using the chain rule as dy dx dx dt. This is what the chain rule tells us, where we're basically treating y as a function of x, where x is as an intermediate variable that is a function of t. So y is ultimately a function of t, but we have this intermediate x variable sort of in between the y and the t. Using this relationship, we can solve for what dy dx is by simply dividing both sides by dx dt. So if I divide both sides by dx dt, we will get what dy dx is. Dy dx is dy dt divided by dx dt. And so in this way, we can determine what the slope of our curve is, right? Rise over run, dy over dx, by looking at the ratio of how quickly y is changing with respect to time over how quickly x is changing with respect to time. We're using the same sort of measure to determine how quickly these two variables are changing independently, and then just simply looking at their ratio. The only thing that's required is our denominator can't be 0. So we can't have dx dt equal to 0. So basically what that's saying is you can't have no change in the x direction. That would indicate that we were basically having a slope of infinity, like a vertical straight line. This is the one case where that formula won't work. And we can do something similar to find the second derivatives. So similarly, to find the second derivatives, we simply need to find d dx of dy dx. But we already have an expression for dy dx right here, and I just need to rewrite the d dx using chain rule this exact same way. So I'm going to write it as d dt dt dx of our dy dx that we already found. You'll notice that this dt dx is really 1 over dx dt. It's the reciprocal of this expression that we found up here when we found dx dt. So I can actually just do a little bit of algebra to rearrange things, and I can just treat this as d dt. We're going to take the derivative with respect to time of the result we got for dy dx. So this result over here, I can just write it as dy dx. You can also write it as all the way out in this format. And then what we're doing is instead of multiplying this result by dt dx, I'm going to divide it by dx dt. And this is the simplest way to find our second derivative. So this is really what it ultimately looks like. So for example, if we have a curve that's defined by the following. So suppose that our x function is going to be t over 1 plus t. And y is equal to the square root of 1 plus t. I want to find dy dx. So again, all I need to do to find dy dx is remember that it's going to be dy dt divided by dx dt, assuming that the denominator dx dt is not equal to 0. So we just need to find those two pieces separately. So we'll start with dy dt, and then we'll find dx dt. So for dy dt, I need to take the derivative of this piece here. So it's d dt of the square root of 1 plus t. We just need to be careful. We've been taking so many integrals lately. Recognize that we're taking derivatives here and don't accidentally do the wrong kind of computation. When I take this derivative, really that's 1 plus t to the 1/2 power. I will wind up with a 1/2 1 plus t to the negative 1/2 power. And technically it's a chain rule problem, right? We're taking the derivative of the square root of stuff times the derivative of the stuff, but in this case the derivative of the stuff is just the derivative of 1 plus t, which is just going to be 1. So this is what our derivative winds up looking like. If you want, you can rewrite that as 1 over 2 times the square root of 1 plus t. But you're welcome to leave it here with a negative exponent instead. And if we do dx dt, that's simply d dt of t over 1 plus t. This is an ugly quotient rule problem. So if we do quotient rule, we've got low d high, excuse me, low d high minus high d low all over the square of what's below. So low times the derivative of the top. So here's the low, low. D high, what's the derivative of that t? It's just 1. Minus high. D low, what's the derivative of the bottom? Also just 1. All over the square of what's below. And if we simplify that numerator, I'm going to get 1 plus t times 1. So this is just 1 plus t minus t. And the whole numerator, basically this t and this t are going to cancel. We're just going to have a 1 up on top. And we have 1 over 1 plus t squared. And if we put these together, it's all one word, together, to get dy dx. So dy dx is going to be the ratio of dy dt over dx dt. And all we need to do is ensure that the denominator isn't 0. That's the one point where this definition won't work. But luckily for us, this denominator can't ever be 0 exactly. So this dx dt, which is going to make up the entire denominator, cannot be 0. So our dy dx, and we'll see that in a minute, is going to be 1 over 2 times the square root of 1 plus t over 1 over 1 plus t squared. There we go. And we'll clean that up. Instead of having a fraction divided by a fraction, I'll do the fraction times the reciprocal, and we will wind up with 1 plus t squared in the top, a 2 square, oops, really mashing that delete button accidentally. There we go. There's our denominator. We can write it that way. Or alternatively, you can recognize really we've got 1 plus t to the positive 2 power plus a 1 plus t to the negative 1/2 power. And that can combine to give us, we've got this 1/2 That's because of this 2 down in the denominator, times 1 plus t to the 3/2 power. We have a 1 plus t squared on the numerator, 1 plus t to the 1/2 power in the denominator. Divide them out, you're left with 1 plus t to the 3/2 power times this extra factor of 1/2 that we have because of the 2 sitting there. So there's our derivative, dy dx. Let's do another example. And obviously, okay, just to be clear, we could take the second derivative by simply taking this result, which is our dy dx, taking the derivative of that with respect to t, and then dividing by the result by the dx dt that we already found, which is right here. So I guess I can just do that real quickly. Let's just say if we wanted the second derivative, so if we want d squared y dx squared, the second derivative, d squared y dx squared, is, you'll recall, d dt of dy dx over dx dt. And d dt of dy dx is just d dt of the result that we just found, which is 1/2 1 plus t to the 3/2. And then we need to divide that by dx dt, which we already found in this line right here. It is 1 over 1 plus t quantity squared. And so our second derivative, taking the derivative of the numerator, this 3/2 will come down, and then we'll drop the power by 1, so we will get, in the numerator, we'll get 3/4. When I bring this 3/2 down times this 1/2, I'll wind up with 3/4, 1 plus t to the positive 1/2 power, times the derivative, again, of what's inside, which is just 1, over 1 over 1 plus t squared. So again, instead of taking this and dividing by a fraction, I will multiply by the reciprocal, and we will get 3/4 times 1 plus t to the 1/2 power times 1 plus t squared. We can simplify that to 3/4. We've got a 1 plus t to the 1/2 and the second power, so that's just a 1 plus t to the 5/2 power. Okay, so there is our second derivative, if we wanted to do that. So first derivative here, second derivative right there. All right, next step. Let's do another example of a slightly different problem. In this one, I want to actually find a tangent line. So let's find the line tangent to let's say x is going to be equal to sine of pi t, and let's let y be equal to t squared plus t. And let's do it at the point 0, 2, which happens to fall on that curve. Okay. One thing we need to do, and it kind of depends on how the question is phrased, is we need to figure out what time this point corresponds to. So what is the value of t? So what time do we pass through the point 0, 2? So we can set either one of these equal, so set this equal to 0, or set this equal to 2, and try to solve. In this case, if I set this one equal to 0, I will get, basically there's a lot of points where sine is equal to 0. It happens at 0, pi, 2 pi, 3 pi, basically any multiple of pi. So that only narrows it down a little bit to be basically having our t here be any integer. So we're going to need to use this one as well when we plug in t equals 2, or sorry, when we plug in y equals 2 and try to figure out what value of t would work. I can just by observation tell it's going to be t equals 1, because I'll get 1 squared, which is 1, plus another 1, which adds up to 2. So this said t could be any integer. Plugging in here, I'll get that t is equal to 1. So this is going to occur at t equals 1. If you don't see that right off the bat, if you can't do it by observation, you can literally just plug these numbers in. So set this equal to 0, try to solve for t, and or plug in a 2 here, try to solve this equation, just using normal algebraic techniques. But in this one, I could see by observation, it's going to occur at t equals 1. So I need to figure out, I have a point, I need the slope at that point. If I know a point and the slope, point-slope form will give me the line. So, and again, I already have the point. I just need the slope. So find the slope. The slope is dy dx, which again is going to be dy dt divided by dx dt. So let's find those values. Dy dt is equal to, so let's do the y one right here. What is the derivative of this with respect to time? So d dt of t squared plus t is going to be 2t plus 1. Dx dt is d dt of x was that sine function, so sine of pi t. What's the derivative of sine? It's cosine, but by chain rule, I'm going to pick up an extra factor of pi. So I'm going to have pi cosine of pi t. And now we just need to know what the value is at t equals 1. So putting these together at t equals 1, we're going to get that dy dx is equal to 2t plus 1 over pi cosine of pi t, and we're just evaluating this at t equals 1, which I'll use that line. Same notation we kind of used for integrals. I'm just evaluating it at a single point in this case, at t equals 1. So this may be new notation to you, but that's all it's meant to indicate is I'm just going to plug in t equals 1. So for us, in the numerator, I will get dy dx is equal to, plugging in 1 in the numerator, I get a 3. Plugging 1 into the denominator, I'll get the cosine of pi. The cosine of pi is negative 1 times this pi, so I'm going to get a negative pi. So there's the slope, 3 over negative pi, or negative 3 over pi. It's a slope close to negative 1 because pi is pretty close to 3. So now that I have the slope, we get that the line is going to be y minus y0 equals m times x minus x0. This is the general version of a point slope form of a line. So m is our slope, and the x0 and y0 are known points. So for us, this is y minus 2 equals m, which is negative 3 over pi, times x minus 0. And that 2 and that 0 come from right here. X equals 0, y equals 2. That's where I got my y0 and x0 values, from the one point that we know. And so we can simplify, rewrite this in our normal slope-intercept form by adding 2 to both sides, and we can get that y is equal to negative 3 over pi times x plus 2. And there's the equation of our tangent line. We can ask other questions. So for example, for which values of t is our given curve concave up or concave down? Is the curve concave, let's say in this case we're interested in it being concave up. And let's say the curve that we're interested in is x equals t squared plus 1, and y is e to the t minus 1. So concave up implies that the second derivative is positive. So we've got to remember back to Calculus 1 where we related the concepts of the first derivative being equivalent to slope and the second derivative indicating concavity. And a second derivative being positive indicates positive concavity, so concave up in this case. So we just need d squared y dx squared to be greater than 0. There we go. That's what we're looking for. So let's find that second derivative. We already said that d squared y dx squared is going to be equal to d dt of dy dx divided by dx dt. And again, we want that to be greater than 0. So let's start by finding dy dx. Along the way, that'll require us to find dx dt. And we can plug this in and find this second derivative. So the first thing I want is dy dt. Then I'll get dx dt. And then we'll put the pieces together to get dy dx and then go from there. So dy dt is the derivative of this. What is the derivative of e to the t minus 1? That's simply going to be e to the t. What is the derivative of x with respect to t? So t squared plus 1, that is simply going to be 2t. And so if I put these together, they tell me that dy dx is going to be equal to e to the t over 2t. So this is basically what our slope looks like. Again, the only caveat is at t equals 0, we're dividing by 0 here. So basically at t equals 0, this thing is vertical. I have this portion now. To cut the second derivative, I need to take the derivative of this result and then divide by dx dt, which we already found. So what we have now is that the second derivative is equal to d dt of the first derivative that we just found, e to the t over 2t. And then I have to divide that whole thing by dx dt, which we also already found right here is 2t. And so if we do this, we're going to have to do, again, our quotient rule on this piece, and then divide by an extra factor of 2t. So I'm going to just write it as 1 over 2t, take that derivative into account, or that dividing by 2t into account right at the beginning. And then let's write out what the quotient rule on this piece is. So again, it's low d high, the bottom times the derivative of the top. So it's going to be 2t times the derivative of the top, which is simply going to be itself, e to the t, minus high d low, so e to the t times the derivative of the bottom, which is just 2, all over the square of what's below. So that's what that winds up looking like. We can clean up this numerator a little bit. There's basically an e to the t that shows up in both terms. It's times 2t minus 2. And we can simplify this to be, so e to the t times 2t minus 2 on top. And on the bottom, I have 2t squared plus another 2t, or not plus another, times another 2t, I should say. And combining these is going to give me 2t quantity cubed, which I could write as 8t cubed. So that's what that second derivative looks like. The question is now, when is this greater than 0? When is it positive? Okay, so this is a little bit tricky, but we can kind of break it down into some parts. So e to the t, for example. E to the t is always positive. E to the t is a function, right, that goes like this. I don't care about the exact values, but I do care about the fact that it's always above the x-axis. So that one little piece is always above the x-axis, meaning it's always positive. So e to the t is always positive. So really, we just need to know when is the rest of that. When is 2t minus 2 over 8t cubed greater than 0? So that's a little bit simpler. Let's think about some different possibilities here. So again, I know that t equals 0 is going to be a problem. At t equals 0, this whole thing is going to be undefined. So let's just see what happens when we do a couple of other cases. So for example, let's see what happens when t is greater than 0 and what happens when t is less than 0. See if we can draw any conclusions from this. And again, t cannot be exactly equal to 0 because this is undefined at that particular point. So when t is greater than 0, what does that tell me about the denominator? When t is greater than 0, then 8t cubed is greater than 0. So we want 2t minus 2 greater than 0. When does that occur? When is this greater than 0? Well, that's going to occur whenever the 2t part is bigger than the 2. So I could add 2 to both sides of this. So another way to see it is, let me delete that period actually. There we go. I want 2t greater than 2, which dividing both sides by 2 implies that t is greater than 1. So when t is greater than 1, this seems to work out because we're assuming t is positive. We didn't get any contradictions there. T greater than 1 is certainly positive. That ensures that the denominator is positive, and we just then focus on the numerator. What about when t is negative? If t is negative, then 8t cubed is also negative. So the denominator will be negative. The only way to make the whole thing positive if the denominator is negative is to make the numerator negative as well. So we would want 2t minus 2 to be less than 0. When is that going to occur? Well, that's going to occur, again, same argument. Now 2t is less than 2, so added 2 to both sides, which implies, that t would have to be less than a 1 in this particular case. So we've divided both sides by 2. Now, we run into a little bit of issue here because in this case, we have this region where it's saying we need t to be less than 1. But over here we have t has to be less than 0. So, for example, if I picked a point that was t equals like a half. If I plugged in t equals a half, we satisfy this. When I plug in t equals a half, the numerator will be negative, like we were wanting here. So if t is a half, then I'll get 2 times a half, which is 1, minus 2 is negative 1. The numerator is negative. But at t equals a half, the denominator is positive. So there's a point where even though we're satisfying this, we're not satisfying this, and we have a contradiction. But we can also check and see what happens if we pick a number like negative 1. Negative 1 certainly satisfies t being less than 0, and negative 1 also satisfies t being less than 1. So let's see what would happen and plug that in. Do we get a contradiction there? It doesn't look like we're going to, so let's just verify that we don't. So if I plug in a negative 1 up here on the top, I'll get 2 times negative 1, which is negative 2, minus 2 is negative 4. So I'll have a negative on the top. And on the bottom, I'll have that negative 1, which gets cubed and gives me negative 1 times this 8, which is negative 8. So I'll have negative 4 over negative 8, that ratio, a negative over a negative, will indeed be positive. So there are two intervals. If t is greater than 1, then both the numerator and denominator will be positive, and the whole result will be positive. So then I should just write, then it's concave up. Our second derivative is positive. Also, if t is less than 0, then it's concave up. In the top case, it's concave up because our second derivative is a positive over a positive, which is positive. And in the second case, our second derivative is a negative over a negative, which is also a positive number and means it's concave up. So we have these two different intervals. These are the two different intervals. So if you wanted to write it as one single thing, you could write it as negative infinity to 0 union with 1 to infinity. It's concave up for that combined interval, where this u just, again, is the union symbol, and it just means we're joining these two together, either this or this. It's concave up on either of those intervals. Okay. Now let's look at some other types of examples. Now that we're hopefully pretty good with slope and tangent lines. Let me find a good one. Let's do... let's do arc length. This will be a good one. Okay, so our next one I want to look at is arc length. So our old formula that we had from a few sections ago is that L, our arc length, is equal to the integral from a to b of the square root of 1 plus dy dx squared dx. And this is if we know y as a function of x, right? So basically, if we have y equals f of x or g of x or something, we have y explicitly solved for as a function of x. Then we use this formula. In the new formulation, we want the bounds to be with respect to time. And we also want to integrate with respect to time. And we want to write everything in here, or the derivative that we've got right here, with respect to time. So in parametric form, everything should be with respect to time. So WRT just stands for with respect to time. So what we need to do is basically figure out what the values of time correspond to being at the x position of A and the x position of B. And so we know that, like, if x is a function of t, so to find bounds, let's do that first. To find the bounds of integration, let's assume that basically alpha, t equals alpha, corresponds to x equals a. So basically what we're saying is that, in essence, if we plug in time equals alpha into our function x, so that x of alpha, x of the particular time alpha, it should spit out the value a. And similarly, let's call t equals beta the time that corresponds to x equals b. And so again, all we're saying is that if I plug in to the function x that we've got, if I plug in t equals beta, I should have it spit out the position of b. That should be the x coordinate that gets spit out. So these are the equations essentially that we're going to use to figure out what alpha and beta need to be. We need to solve these equations. We'll have a and b, we'll know what x is, we'll have to solve for what the alpha and the beta are. Similarly, I'm going to have to come in and rewrite all these other pieces. So again, we know what dy dx looks like, but I need to figure out what dx is by itself. So if we go back, so now we need to solve for what dx looks like. We found the bounds, now let's solve for what dx is going to look like. To solve for what dx is going to look like, I want to kind of remember that our dx, if we write it in terms of, let's say this way, that dx is really going to be dx dt times dt. That using our Leibniz notation, dx, if x is a function of t, we can write it as dx dt using our chain rule. So this is the way that we're going to solve for what dx is. And we also need to solve for, and I'm saying solve for, maybe that's bad wording to use, but how do we represent dy dx? So solve for, I should say solve for dx in terms of t, again, or dt in this case. Same thing, solve for dy dx in terms of t. I want it all in terms of t. And that we already did. Let me just remind you, we're just using the formula we've already used, that this is simply dy dt divided by dx dt. That's it. And alternatively, you could think of it, if you change it into a multiplication problem, as, again, dy dt times the reciprocal of this, so times dt dx. That's one way to think about it if you'd like. And that might help us just down the line a little bit, help us with some simplification. So this is normally how we think about it, but just recognize you can write it this way in Leibniz notation. These represent equivalent things. So if we put these all together, and again, all I've done is started with this formula and figured out how do I convert every component of this to be in terms of t instead of in terms of x. So we know what our new bounds are going to be. They're going to be alpha and beta that we can find by solving this equation for alpha and beta. I'm going to swap in the dx to look like this, and I'm going to swap in the dy dx to look like this, or alternatively this, if it suits, or if it's beneficial to do so. So if I put these all together, we get that L, our arc length, is going to be the integral from alpha up to beta of the square root of 1 plus that dy dx squared. So I'm going to write it as the dy dt times dt dx squared. And then I have that out here times dx, which was dx dt dt. So here are all of the pieces. What I want to do is basically roll this piece into the square root. I want to, right now it's outside of the square root, I want to move the dx dt into the square root. And to do that, I would basically have to move it in there, but it would have to be squared when I move it in there. So what do I mean by that? What I'm suggesting is, what I'm going to do is take this 1 plus, we could write these individually. If we're squaring this product, I'll just write them separately. Whatever, I'll just leave it as is for now. So there's everything inside. I want to move this other piece inside, but to move it inside, it would have to be dx dt squared times dt. So all I've done is move this inside the square root. But because it doesn't have an existing square root, I want to basically write it as the square root of dx dt squared. And then I can move this inside the square root, combine the two radicals into a single radical. So that's what we're doing there. Okay. If we distribute through, this is going to be a lot nicer. And I'll get the integral from alpha to beta. I'm going to have, when this part gets distributed through to the 1, it's just going to be dx dt squared. And then I'm going to distribute it through to this part. And so over here I've got dy dt squared times dt dx squared times dx dt squared. But by design, these two fractions here are reciprocals of one another. And because of that, I'm going to get them to cancel out, right? We could think of this as we're going to get a dt squared in the numerator, and we're down here going to get a dt squared in the denominator. We're going to get a dx squared in the numerator here, but we're also going to get a dx squared in the denominator down here. So all those pieces will cancel. And what we'll be left with is simply the integral from alpha to beta of a nicer looking formula, dx dt squared plus dy dt squared dt. And honestly, in a lot of ways, this is kind of an intuitive formula. If you think about the curve that you're following, you're wanting to find a piece of arc length from here. This is some small increment of some delta t that it takes. Really, if I want to approximate that distance, I would just use the hypotenuse of the triangle there, where we've got a little bit of change in, right, here's our dx dt squared, here's our dy dt squared, and then I have to take the square root of the sum of the squares here and then multiply by dt to get rid of the denominators here, right? What I really have is dx dt. So I have a rate of change, but if I multiplied it by dt, right, so yeah, let's write it this way. There's a little dx, here's a little dy, and I'm cheating here just to make this go a little faster. Here's the little change in amount of time that it took to get from there to there, and I want the approximate distance. So this distance is our dl, a little change in the distance. And so that little change in distance is going to simply be the square root of the dx squared plus the dy squared. But because of these both being related to derivatives, instead I can write that dx dt squared plus dy dt squared square rooted, and then multiply by that dt outside. This dt outside of the square root will cancel with the dt's that are inside the square roots in the denominator. Essentially what we're saying is if I want the length, the distance squared, I can take the two velocities and then multiply by the amount of time. Right? If I want a distance, all I have to do is take the rate, which is our derivatives, and multiply by time, our d equals rt formula. And that's what we're doing here. This t, the little bit of time, is dt, and the rates in here are the derivatives, and we're taking the square root of the sum of those squares to get sort of the velocity right here. That's the idea. So big picture-wise, you don't need to know all of this, but that's all this formula is saying, is if I take the two little velocities and use the Pythagorean theorem, it'll give me basically the velocity in this direction, the speed that I'm traversing sort of in the tangent direction along here to here, then multiply by a small of increment in time, and that'll convert it into a little bit of distance. Then we'll just sum up all those little bits of distance to get the total arc length. Hopefully that makes some sense. Okay, but end of the day, oops, this is the formula that you need to know. So, as an example, maybe I want to find the length of C from t equals 0 to t equals 1, where the curve C is defined by the following parametric representation. X is equal to 1 plus 3t squared, and let's say that y is equal to 4 plus 2t cubed. And so if I want the arc length, all I need to do is integrate from the starting time 0 to the end time of 1 times the square root of, again, dx dt squared plus dy dt squared, whole thing square rooted, times our dt. So I just need those two expressions. I need that and I need that. Let's find those two derivatives. Dx dt and dy dt. So dx dt is going to be the derivative of this with respect to time. I can see right away that that is just going to be 6t. For the other one, I want the derivative of this with respect to t. Again, the constant isn't going to contribute, but this 3 will come down and it'll get 6t squared. So there's the derivatives, and we just need to plug them into our formula. And we're going to get that L, our arc length, is going to be the integral from 0 to 1 times, the integral from 0 to 1 of the square root of dx dt, which was 6t squared, plus the other one, which was 6t squared, dt. And we can solve this integral. Let me actually evaluate or basically expand out these terms here. So I'm going to get the square root of 36t squared plus 36t to the fourth. Alternatively, we could have thought of it as factoring out a 6t squared from both of these. We'll see that in a minute. So however you want to factor this out. But basically, I want to recognize I've got a 36t squared in both of these. So I can think of this as the integral from 0 to 1 of the square root of 36t squared times 1 plus t squared dt. But these can be broken up. I've got the square root of a product. Right? What I'm going to do is basically say that the square root of ab is equal to the square root of a, square root of b. And so this is equal to the square root of 36t squared times the square root of 1 plus t squared dt. But what does this term out here? The square root of 36t squared is simply 6t. So I'm going to have 6t times the square root of 1 plus t squared dt. Okay. Whew. So after all of that, I've got a u substitution problem. Inside here, the derivative of this stuff inside the square root is going to be a 2t. I have a 6t out here. So if I just change this to a 3 times the integral from 0 to 1 of a 2t, in fact, let's maybe even write them in a different order. Let's write it as the square root of 1 plus t squared times 2t dt. Then all I need to do is let my u be equal to 1 plus t squared. That means that du will be 2t dt, which is exactly what we've got right here. I can plug in my bounds So if I want to figure out what like u of 0 is, so plug in x equals 0, and then find out what u of 1 is. Sorry, not x, of t equals 0. So I'm plugging in t equals 0 here, and I plug in t equals 0 to my u, I will get 1. When I plug in t equals 1, I will get that u is equal to 2. And so my integral is going to be 3 times the integral from now 1 to 2 times the square root of u du. And if we do that integration, I've got my 3. The square root of u is going to integrate to u to the 3/2. I need a 2/3 times that. And we're evaluating between 1 and 2. And I can get a little bit of cancellation, and I will wind up with 2 times 2 to the 3/2 minus 1 to the 3/2. However you want to write that, this is, if I cube this, I'd get 8, and this is would mean we're taking a square root, so you could write this if you wanted as 2 times the square root of 8 minus 1. And this is, whatever units of length we're dealing with. So if the original problem is in terms of inches or feet or meters, we'll have those same units, but we've got to keep that in mind. These would need to be defined in some units of position. And if you think about position, it's really lengths, the length from the origin to the x-coordinate, the length from the origin to the y-coordinate. You'd have those same lengths. Okay, so that's how we can find an arc length. Let's do like a surface area, I guess. So let's do surface area. So the surface area of a curve C, again, rotated about some axis. So in this case, if it was about the x-axis, for example, our old formula for that was that the surface area, we'll call it capital S, was 2 pi times the integral from a to b of f of x value times the square root of 1 plus f prime of x quantity squared dx. So this was the old formula that we had, one of several we had for surface area. We had different versions depending on whether you're rotating about the x-axis or the y-axis. But this is just a formula copied from a couple of chapters ago. So if we keep in mind what we're trying to do here, all the same changes that we were just trying to make, this portion was meant to represent something that gives us our little bit of arc length. So this has units of length. This is essentially just the y value. It's the y coordinate. It's the height of our curve. But now the height of our curve is given by y of t. So I need to convert everything to be in terms of t. So in terms of t, what we're going to get is that this same formula, s, we're still going to have the 2 pi, that hasn't changed. Our bounds of integration are now, instead of between the x position a and b, it's going to go between time equals alpha and time equals beta with the same definitions we used before for those two values of time. And it's simply going to be the y value, so y of t, y is a function of t. And then our arc length is now written as dy dt squared plus dx dt squared dt. So this follows the same, I'm not going to go into all the details, but this follows the same idea, right? This was meant to represent the arc length. Now this is the arc length. This represented a height. Now y itself is a function of t represents the height. And instead of integrating with respect to x, we need to integrate with respect to time. So that's all of the changes. And you would have a similar one if you go back and look at the other surface area equation for rotating about the y-axis. Has an equivalent form just like this. So let's do an example, because I think that will be the most helpful. Let's find the surface area of basically the curve given by the following. So let's say x equals 2t squared plus 1 over t, and y is equal to 8 times the square root of t, with 1 less than or equal to t less than or equal to 3, rotated about the x-axis. So here's my parametric representation of my curve. Here's the values of time I'm interested in, and we're rotating about the x-axis. So this is the formula, which I guess I should put a big box around. This is the formula that we need. So S, our surface area, is going to be equal to 2 pi times the integral from alpha to beta, so for us that's 1 to 3, of y, right, the height, which is already given right here, 8 times the square root of t, times the square root of these two pieces. So we need the derivatives of this and this. So let me just plug those in. Let's find them right down here, and we'll plug them in. So let's find dx dt and dy dt. So dx dt, the derivative of this one, when I take that derivative, I'm going to get, what will I get? 4t, and the derivative of 1 over t, you can think of that as t to the negative 1 power. The negative 1 would come down, and the power would decrease, so you can think of it as minus t to the negative 2 power. And then for dy dt, the derivative of this, that 8 just sits there. And we've got t to the 1/2 power, so that 1/2 will come down. And the power will decrease by 1. So that's what we've got in these two cases. So those are what I need to plug in. I need to basically square those and plug them in. If you want, you could rewrite this as like 4t minus 1 over t squared. And you could rewrite this one as, what is that? 8 times 1/2, so that'll be 4 times, I guess it'll be 4 over the square root of t. If you want, you can write that that way. So we're plugging those in, the squares of those in rather, to our formula. So I'm going to have my 4t minus 1 over t squared plus 4 over the square root of t squared dt. So I've simply plugged this right here into our formula in those two positions. And I guess I got them mixed up. So either way, dx dt squared, dy dt squared. I changed the order compared to this one. Doesn't matter. Okay, this looks awful. How are we ever going to integrate this? But by design, again, to make it so you can do these problems by hand, they're always designed to work out with a whole bunch of nasty algebras. So that's all we need to do now is figure out what ugly, hideous algebra do I need to do to make this workable. So we get, and again, in real life, maybe you need to solve this numerically, but for the ones on the homework, for the ones in here, on the exams, quizzes, examples that we do, they'll always be designed to work out so you can still do them by hand. So our S is going to be equal to 2 pi times the integral from 1 to 3 And let's start seeing if we can clean this up. First thing I want to do is merge these together. I want to basically multiply this square root of t on into the other one. So we'll have our 8 here. I'm going to write this all as one big square root. So this is going to be a t times, so this t came from this t inside the square root, and now I'm going to FOIL this piece out, and I will get 16t squared. I will get this times this, so 4t times negative 1 over t squared will be just 4 over t. Right, so I've got 4 over t, but then I'll have another 4 over t with a negative sign, and we're going to get a total of negative 8 over t. And then this one times itself will be plus 1 over t to the 4th. Okay, got all of those pieces. So that's just this FOILed out with this t sitting here in front of it. Do the same thing to this one. I'm going to have a t sitting in front of it, and we'll get 16. When I square this, I'll just get a t in the denominator. So 16 on the top, a t in the denominator, dt. Let's toss parentheses around it. So this is just this thing squared. Okay, we'll distribute those t's through and then see if we can simplify by collecting some like terms. We can pull this 8 out in front if we want to as well. So I'll write this as 16 pi times the integral from 1 to 3 of the square root of, distributing that through, I will get 16t cubed. This next one's nice. It's just minus 8 because the t in the numerator cancels with the t in the denominator. And then the last one, I'm going to get 1 over t cubed. And then for this one, again, the t's will cancel, and I get plus 16. So we'll collect our like terms. I've got my 16 pi integral from 1 to 3. Let's collect those constants and put them in the middle, and I'll have 16t cubed plus 8 plus 1 over t cubed dt. Okay, and this is still looking a little bit scary. It's not looking great, but the whole idea is we really want to try to simplify this. We want to turn this into, if at all possible, a perfect square. And what we should recognize is that the way the powers are separated here, they're all separated by 3, right? This is t cubed. This is a constant, so it's basically t to the 0th power. And here I have t to the negative 3rd power. So whenever they're separated in a nice even way like that, with the same increment of 3, increment of 3, there's a chance that we're going to be able to kind of do some nice stuff to this. So think of it this way. What I want to do is I basically want to multiply this whole thing by t cubed. So let's multiply the whole thing by t cubed. But I can't just multiply by t cubed. I'm going to also have to factor that out in the front in the following way, because we can't actually change the value. We can't just magically introduce a t cubed. But if I were, let me leave some space in front. If I were to multiply through inside the square root by t cubed, I would wind up with 16t to the 6th plus 8t cubed plus 1. But that was multiplying, again, by t cubed on the inside. I have to make up for that by then dividing by t cubed as well. So I can think of that as times square root of 1 over t cubed that I need to be able to basically pull out of this thing. dt. So again, I multiplied by a t cubed on the inside, and I also had to multiply by a 1 over t cubed on the inside, but I pulled that off as a separate square root piece. So essentially what I have here is I multiplied by t cubed times 1 over t cubed. The whole thing, it was inside the square root, so basically that's what I did. This part got put in there, this part wound up separate right there. That's all I did. So I multiplied by 1, a really ugly form of the number 1. Okay, we're getting closer, but we're still not there yet. But again, follow this technique. It's ugly, but this is the technique that you will see. These will all be designed, and they'll almost always follow a pattern very similar to this. Okay, so this piece right here, I'm going to just have come sit out front. We could think of it as t to the negative, 3/2 power if we wanted to. I guess I could write it like that. So t to the negative 3/2 is how we could write that. Times this square root. But notice that this square root, or the stuff inside this square root, is now a perfect square. And that is going to be our goal. They're powers of, in this case, something involving a t cubed that is being squared. So I can write what's inside that square root as a 4t cubed plus 1 squared. And this is, again, by design on these problems. It's contrived, but all of these homework problems are contrived to work out in such a way that something like this will happen. And let's just verify. If I FOILed this out, I'd get 16t to the 6th when I multiply this by itself, exactly what we've got. I'd get a 4t cubed plus another 4t cubed. There's my 8t cubed. And then I'd get a 1 times itself, plus 1. So now I've got a square root and a square, and we can kill that piece off, basically. And we will wind up with my 16 pi integral from 1 to 3 t to the negative 3/2 times the square root and the square cancel, and we just get 4t cubed plus 1 dt. Okay, now this is looking like something that we can actually handle. Basically, again, our goal is to get rid of the square root. The square root is what makes things hard. So if we can find a perfect square in there, if we can recognize a way to turn it into a perfect square, then we can cancel the square root with that perfect square. That is always the goal in these problems. Integrating with square roots is hard. Is there a way to get rid of that square root? And so we found the way. So now all I need to do is basically distribute this through. And we will get 16 pi times the integral from 1 to 3 of distributing that through. I'll get 4. I've got t cubed times t to the negative 3/2. When I multiply those together, that'll give me a t to the positive 3/2. That's what's left there. Plus, when I multiply it by the 1, I'll get t to the negative 3/2 dt. So after all is said and done, this mess right here turned out to be the same as this mess right here. These two things are equivalent. Just took us some semi-unintuitive algebra to get there. So I'm going to break that up into our two separate integrals. We can actually do this integration now. I'm going to get my 16 pi, the integral of 4t to the 3/2. The power will go up to 5/2, and I'll need a 2/5 to cancel that. So I'll have 4 times 2/5 t to the 5/2. And then to that, I'm adding, same thing, integrating this one, the power will go up. It'll become t to the negative 1/2, but to account for that, I'll need a factor of -2. We're evaluating between 1 and 3. And so we'll just plug these numbers in. It's not going to be pretty. It's going to be a big, ugly number. This is, at this point, something you can do on the calculator, essentially. But plugging in that upper bound, what is that? 8/5 times 3 to the 5/2 minus 2 times 3 to the negative 1/2 minus doing the same thing, evaluating at the lower bound. Here's that big ugly number. Luckily these are easy, they're just 1, 1. So that's going to be relatively simple. But these other ones, if you want to think about it, you could think of this as square root of 3 raised to the 5th power. That's the same as basically, so square root of 3 squared would be 3, just basically root 3 times root 3 times root 3 times root 3 times root 3. That's what we've got sitting right there. And so those will give me a 3, those will give me a 3, and we wind up with 9 root 3. So that's going to give me 9 root 3. Oops, let's erase this. Root 3 times this 8/5. And over here, we're just going to get a 2 over root 3 minus 8/5 plus 2. All right, so this is our big ugly thing that we've got to find a common denominator. So I've got to find a common denominator. These both have 5s. Got our 9 root 3. Common denominator, we can just make b like a 15, I guess. And we could rationalize this one and write it as root 3 over 3. We can make the denominator be 15, and again, this is hopefully not wasting your time too much. If you want, just fast forward until we get the answer here. So multiplying this times 3, I've already got 72, so this is going to be 3 times 72 root 3 over 15. I multiplied the 8 and the 9 to get the 72, and I multiplied by 3 over 3 to get the 15 on the bottom, and that's what this 3 up here is doing. Same thing, I'm going to multiply by 5 root 3 top and bottom, so I'll get minus 10 root 3 over 15 minus 8. Let's do that one right in terms of 15ths. So times 3 over 3 is what? 24 over 15 plus 30 over 15. 3 times 72 is going to be what? Like 2016? Not 2016, 216? Is that right? I think 216. So I've got 216 root 3 minus 10 root 3 minus 24 plus 30 over 15 times 16 pi. And so I will get 16 pi times 206 root 3 plus 6 minus 24 plus 30 is plus 6 over 15. Is that right? Did I get all the signs correct, maybe? Hopefully. I think so. So that's, I think, what I get, unless I made some dumb mistake somewhere and miscalculated things, but I don't see it. So anyways, really, again, this is all unnecessary. Get it to here. And maybe do these simplifications. I don't need 1 to the 5/2 and 1 to the negative 1/2 written as anything but ones. So maybe this line-ish would be a totally fine final answer. Something like that. Or plug it into the calculator and just get a decimal. So that's what we're looking at. But this has units of, again, it's surface area, so it's going to have units squared, length squared, whatever that happens to look like. Maybe one last example. Let's do one where we try to find area instead of surface area. And let's see if we can work this out. So let's find the area enclosed by the curve given by x equals t squared minus 2t, y equals the square root of t, and the y-axis. So let's just pretend we know what this looks like. I have no idea what it looks like, but let's just say what the suggestion is, that this thing must cross the y-axis in a couple of places because it's enclosing some region. So let's find where this crosses the y-axis. That's the implication. It's doing some sort of thing where it crosses it. So what I'm saying is we've got our y-axis and we've got this curve, and whatever it happens to do, it must cross it at a couple of points. And this is the area that we want to find. Or let's say this is the x-axis. So let's find these points. The y-intercepts. Well, the y-intercepts are where x, the x-coordinate, is equal to 0. So we just need to plug in x equals 0. So the y-intercepts occur when x is equal to 0. So where is x equal to 0? Well, let's see. It's going to occur at these points, which I can rewrite that as t times t minus 2. And it looks like what we're suggesting is, there we go, is that t must be equal to 0 or 2. So those are the two different bounds in t. So that's going to give us our bounds of integration in t. And let's think about how this is going to work. If I want the area, what I want is basically a bunch of little rectangles like this. That's one way to think about it. Right, we've got some little vertical measure, dy, which can be a function of t, possibly. Maybe it's a constant. And then we have this distance, the width here, and that distance there is going to be our x of t, right? It's the distance from 0 to whatever that x coordinate happens to be. And if I multiply these together, so the area of that little rectangle is going to be x of t times dy, which again, we've got to remember is a function of t, from some t0, some starting point, up to some endpoint t1. So that's what we want to do. And so how do we write this? Our area, adding up all of these, this is for one little rectangle. We want to add them all up, and we will get the area is going to be what? The area is going to be the integral from our starting point t0 to our ending point t1 of our x of t times our little dy. But we can write that, because we need to integrate with respect to t, not with respect to y. I can write that as dy of t dt times dt, right? This dy of t can be written as dy of t dt times dt, dividing by dt, multiplying by dt. That turns this into a derivative. So this is really the same thing that I have right there. Okay, so this is what our formula is going to wind up looking like. So for us, we just found the starting and ending times as being 0 and 2, assuming we're going from here up to there, right? So that our y goes in the positive direction. And that means that, oops, come on. I need my x of t formula. Let's get this all on the page at once so I can see everything that I need. So I need x of t, which I've got right here. So that's going to be t squared minus 2t. And then I'm going to multiply that by dy dt. So here's y of t. So what is dy dt? It's going to be 1/2 t to the negative 1/2. So 1/2 t to the negative 1/2 dt. So one thing that I want to keep in mind is, if we're trying to find the area, it assumes that this x of t needs to be positive. we're going from t equals 0 to 2. If I were to plug in a value somewhere in that interval, so for example, plug in t equals 1, what do we get for this when I plug in t equals 1? When I plug in t equals 1, I'll get 1 squared minus 2 times 1. So I've really got 1 minus 2, which is negative 1. This value is negative on the interval from 0 to 2. I drew it wrong. I drew it as going into the positive x direction. This graph actually is over here on the left. And so technically, this width, instead of being the x value, it needs to be 0, the right side, minus the x value. It needs to be the negative of this. Ultimately, we'll need to flip the sign. So technically, this is negative. So we can just flip the sign at the end. But we can anticipate that because if I actually check this x value, if it's in the positive side, then we're good. But if it's over here on the negative side, I can't just use x by itself because it would give me a negative value. I want the unsigned version of this. In a sense, you could think of doing like the absolute value of this quantity here. So that's really what we need. We're going to get a negative value. We'll just need to flip the sign at the end. So keep that in mind. Look out for things like that. If you get an answer for an area that's negative, probably made a mistake with your sign. So just go check and make sure that it wasn't something as simple as you thought your curve was in the positive x area, but it turned out to actually be in the negative x region. Okay, so we will distribute through here. I'll get the integral from 0 to 2 of, let's see, that first one will be 1/2 times t to the 3/2 when I do t squared times t to the negative 1/2. And then the next one will be the negative 1/2, or sorry, the negative 2 and the 1/2 will cancel and leave me with just a negative 1. And I'll just get simply t to the positive 1/2 dt. So that was just simply distributing this term through to both of these. Now we do our integration, and I will get, this is again going to be t to the 5/2. I'll need a 2/5. I already had a 1/2 there. For the other one, it's going to be t to the 3/2. I need a 2/3 to make up for that. And we are evaluating this between 0 and 2. And if we plug that in, again, I can do a little cancellation here, cancel those 2's at least. I will get 1/5 times 2 to the 5/2 minus 2/3 times 2 to the 3/2. And then when I plug in 0 in both of these cases, I will get 0. So always check the 0. Don't just assume you'll always get 0. That was a common mistake I saw on the exam. So here's the results. We can figure out what 2 to the 5/2. Again, that's just a bunch of square root of 2's. So root 2 times root 2 times root 2 times root 2 times root 2. That's how you can think of this. This will give me a 2. This will give me another 2. I'll have 4 root 2 when that's all said and done. And we will get 1/5 times 4 root 2 minus 2/3 times, this one is 2 root 2. And we've got a root 2 that we can factor out of everything. We've got to get a common denominator. Let's see here. Let's do a common denominator here. So just real quickly, times 3 times 5. And we will get, what is this? 12 root 2 over 15 minus, this is a total of 4. When I multiply by 5, so I'm going to get 20 root 2 over 15. And sure enough, we get something negative. We get negative 8 root 2 over 15. And if we, let's see here, is that right? Hopefully I didn't screw this up. Flip the sign. To get 8 root 2 over 15. units squared. Let me just make sure I didn't do an obvious mistake here. Nothing that I see, at least. And so I'll just assume that hopefully I didn't screw that up. All right, well, that's pretty much it that I can think of for this section. So again, once you know how to manipulate, basically represent curves parametrically, there's just some basic manipulations to get these formulas. You don't need to rederive these. Oops. But here's a formula for arc length. There's a formula for surface area. We had a formula up here somewhere for the tangents, so the derivatives and second derivatives. Use all of those with the appropriate applications, and hopefully you won't have to worry too much about the arithmetic at the end. Use a calculator whenever you can.